questions on what we covered previous to this? You got the concept. You got identification. Here is syntax then. I have all of the syntax everywhere. Could you make sure the door is shut too, please? Sorry. Thank you. You'll note the first 6 rows of my syntax here are all the regressions, right, with the single value for the tilde. Right? So this is performance was being predicted by 3 variables: high school experience, math concept, and math self-efficacy, and so forth. The other ones are mostly implied, although I will note, if you don't go through the time to put the zeros in the covariances, it'll put 1 to 2 of those in for you that you may not want there. Right? These are residual covariances, and what it seems like there's no rhyme or reason, but if you go through the whole path model itself, any endogenous variable that doesn't predict anything else is given a covariance with all the other endogenous variables that don't predict anything else. Why that one, I don't know. It seems a little weird to me, but that's what shows up if you don't zero that out. This is a hint for homework this week. All right? It's a good exercise to get in for this reason. You know how many parameters you should have. You run it. It tells you how many parameters were in the analysis. This is a good double check to make sure it's doing what you expect it to. The reality of it is if you drop one parameter from it and the model fit's questionable, then the other parameters change. Right? And that's the weirdness to it. If you have too many or if you have too few, your results change. Oh, that's terrible. So everything else is there. Any question on syntax? Questions? I feel like ever play blackjack at the casino? Anybody?
Oh, we're not supposed to admit that.
Hey, you know, my story is school taught me to gamble. And you'll hear about this in the next couple of weeks if you haven't heard it already. I know those of you, some of you brave souls have had me 3 times in class, which is probably 2 times too many, or maybe even 3. You'll learn why. But it was because of school that I played blackjack. And yes, insurance is open. Questions are open. Questions are closed. So if you don't know my reference, if you play blackjack in the casino at 21, when the dealer gets an ace card, so each of you has 2 cards. You have your 2 cards nobody sees. The dealer has 1 card up and 1 card down. If the dealer has the ace up, that means if the card below is a face card or the number 10, they win, always. They take all of your money. All right? So they offer you insurance, which is a side bet that if they do have a 10 or a face card underneath, then you win something while they take the rest of your money. And I can't remember what the values of it is. All I know is the math behind it is terrible. It works out very badly, and I never buy insurance. I rarely see people who do, but they ask it every time. They kind of like they have this little mirror. They put the card under. They see what their card is, so they know. And then they go, oh, insurance is open. And they kind of put their hand over the table because the eye in the sky is watching them ask everybody. And if you don't move your hand like yes, then they put back, okay, it's closed. This is me with questions. Questions are open. Questions are closed. Okay. Questions are insurance. Awesome.
You just told us that insurance is a horrible bet.
It's a horrible
You made an
bet.
analogy with questions.
I did. I would actually, questions are much better bet than insurance. Bad analogy. Not a metaphor, maybe, but more just I feel like the dealer here. Oh, no. It's getting worse. Okay, last week I told you when I was on drugs, and so... Okay, back to statistics. I took this syntax, I put it into the SEM function, and then I did the summary function, and sure enough, the first thing that popped out, it converged normally after 78 iterations. So if you think about that little flow chart, I achieved convergence. What's my next step? Check model fit. All right. Model fit statistics. Remember those from last week? Oh, those were the days. We looked at likelihood ratio tests with your model and the saturated model. That is right up here. we see there is a difference of 9 degrees of freedom. And sure enough, we counted that, right? We saw there were 28 parameters in the saturated model's covariance matrix, and there were 9 in our terms that went into it. Any model parameters that wasn't an intercept or a mean. There's or 19, excuse me. 28 minus 19 is 9. Yes, 9. I can do math. Math is hard. There we go. So the p-value for that's 0, which means we reject the null hypothesis. The null hypothesis is our model, essentially. All right. So if we were going by likelihood ratio test, we would describe our model doesn't fit. But thankfully, we don't like that, because in SEM, proof in statistics is meaningless. We just want to know it close enough to good enough fit. Sorry, I'm being tongue-in-cheek there. Remember I told you that's one of the debates about model fit. Statisticians would look at this and be like, we can't use these results. In fact, if you're over in a multi-level model, you'd probably be like, no, we're not using these results. But here in SEM world or path analysis world, we might use these results. So we go down and we start looking at the CFI and the TLI. The CFI, remember, these are indices, so they must be high. We want them high as possible, and usually 0 to 1 is the range they fall in, although they technically can go other places. 0.91 and 0.809 are the values. We'd like them to be bigger than 0.95, so that's not good, though I've seen them published. Actually, I asked you this last week. Did any of you look at papers in your field that did path analyses or SEM by any chance? Did you see model fit reported? No. If you ever have a chance to do this, that'd be awesome. This is more just for my own, oh yeah, what's common in your field? Because each field's a little different. But the trend is always weaker model fit makes publish because of those extra boxes I put: publish or Paris, grant funding, tenure, all the things that we talk about that are good. So there's those numbers. The RMSEA is 0.126, which we want that to be less than 0.05. Remember, root means small, that mnemonic. It is not good. And then the standardized root mean squared residual. We usually somebody said 0.08 or less. I think it was the Yuan and Bentler article. No, but I just don't look at it if the rest of them don't fit. I just don't like that thing. But I would say, hey, look, it fits. That would be a very weak and tenuous case for model fit. So we're the part of the flow chart, the path diagram of path analysis that says, did model fit? I would say no. And besides, I should be teaching you the lofty expectation, right? This is the ivory tower. I used to work in an ivory silo. That was in Nebraska. Sorry. Anyone from Nebraska? Sorry. Just, you know what I'm talking about, right? Sorry. It's supposed to be a joke, right? We should have these lofty expectations about fit, when really, pragmatically, it's not quite. But this is bad regardless. So we're now going to look to modify our model. And last week we talked about modification. We talked about two methods. They kind of fell into the local fit area, right? Whereas all the things on the first slide here, all the fit statistics are global. It says overall we don't fit. Local is kind of an inspection to say where is the fit bad. So we can look at our residual matrix. This is our residual covariance matrix, right? It's what our model implies the covariance should be, or the matrix, versus the saturated model covariance, right? So it's a term residual. We throw the word residual around like it's free, but it's just not of data and not a residual variance. It's the difference between saturated model covariance matrix and what your model's covariance matrix is implying. So the bigger the difference, I use the word normalized there. This is in the residuals function. Normalized I like because these values are like z-scores. All right? We want these to be not significant z's. If they're big or small, it's like a z-score. You would reject the null hypothesis that they fit well. And so here's a value of 5.51. That is the covariance between math self-concept and perceived usefulness. Because it is bigger than 1.96, we'd say, yeah, that's a significant value. It's significantly bigger than 0. We want these all to be 0. But if they're not 0, if we put in sampling error and model error and so forth, what would the value be? That's what it's telling us. Similarly, if we look at gender versus college experience, there is a significant negative residual covariance between them, between gender and college experience. So if I didn't know anything about theory, and that's why the big bold underline is in the middle of the slide to remind me to say, generally what we're about to do should be guided by not just the numbers, but also empirical hypotheses about your data. Right? I'm not a math educator. I don't know much about it. I have worked with some of them before. Actually, some of the colleagues I hold in most esteem for the rigor in science, not just for quantitative but also qualitative research, mixed methods research, are math educators. They are fantastic at who I've worked with. So I look at this and I think, if I'm going to start making changes to my model, I need to have a good substantive or empirical reason as to why I would change it. But what these are suggesting is, if we were to go and put something in the model that would relate these two variables together, it would work. So, for instance, here, now my pen, battery, something, come back to me. There we go. This one, we would need something in the model that modified the relationship between usefulness and math self-concept. That can be almost anything. We're going to look at the slide in just a bit. This one would imply we need something in the model to kind of modify the relationship between gender and college experience. Right. So let's take a look a little bit more. The other thing we can get out of this is modification indices. Remember, these were magic or voodoo, depending on where you're looking at. One person's magic is another person's voodoo. Did anyone celebrate, speaking of voodoo, it makes me think of New Orleans. Did anyone celebrate Mardi Gras yesterday? Or maybe you're celebrating Lent today, Ash Wednesday, perhaps. Maybe. I don't know which one we celebrate more, maybe both. When I grew up, my grandmother was from Great Britain. We used to call that Shrove Tuesday instead of Fat Tuesday, whatever. I don't know, weird name. We'd have all sorts of really bad food on that day. Evidently, she was training me for New Orleans. Has anyone been to New Orleans on Mardi Gras before? I have. It's an amazing experience. One was for a conference, an academic conference. It started on Mardi Gras in New Orleans. And my first experience, I was driving from Illinois to get to New Orleans. I was a grad student, didn't have a lot of money. I was trying to help my professor out. He was running the conference. Yeah, I drove. That's like, well, good effort, right? Anyway, I drive into New Orleans, and I see a guy walking across the street in a half of a Barney outfit. He's the purple dinosaur on a crosswalk. I'm like, oh, this is just how it is, right? Anyway, I digress. Modification indices are voodoo or magic, depending on how you look. These are indices that tell us if we were to have added a parameter, what the likelihood ratio test with the model with that parameter versus our current model would have been. Right? So if you think about it, if we add the parameter, we have a new alternative model that has one more parameter, one more degree of freedom in a comparison with our current model. So if these values, which would be values that are chi-squares, are bigger than 3.84, we would think, oh, that new model would fit significantly better with that parameter. Here are three parameters that relate the two of the variables together. Remember, two of our variables, math self-concept and usefulness. Here are the three that have that, right? We could put in a covariance, or in this case, a residual covariance between the two. We could put in a kind of a prediction. We could say usefulness is predicted by math self-concept. Or we could put in the opposite prediction, that math self-confidence or concept is predicted by perceived usefulness. And this is where it gets all whack, because all three of those give us roughly the same value. And all three of those modify the model in an almost indistinguishable way. But they are working together with our residual covariance that you see on our previous slide to say, yeah, that's the biggest thing we need to concern ourselves with. We need to go and add one of those to our analysis. Right? So this is where the substantive hypothesis or the empirical knowledge of mathematics education would come in handy. If you're working with somebody, or if you are the math educator and you're like, well, wait a minute, does your self-concept of mathematics affect your how you think it's usefulness? Seems plausible. Or is it the other way around? Does whether or not you think math is useful make you have more or less math self-concept. Right? That's what both of these two are implying as a hypothesis. I don't know the answer. Do you? So we can go with option 3, the agnostic. Yeah, one of the two of those works. We don't know which one. Let's let them covary and call it good. All right? So we add the residual covariance, and it's less of a strong hypothesis. And I mentioned before, the residual covariance is like a throwaway parameter, right? We just throw it away. So here is math self-concept and perceived usefulness. Sure enough, they are able to have a covariance between. So it still doesn't induce a cycle. Now, some of these, if you just go by these modification indices, some of these are ridiculous. Some of them can't be added, otherwise it will break your model, but you can still get them to work because of the mathematics behind them. You can get a number for them, but if you add them, all of a sudden you move to an unidentified model. So you have to really know what you're looking for, I feel like, before you go snooping through modification indices, and that's why I show you both of these. Residual covariance and model, so forth. Let's take a look at this other one, though. There's supposed to be something between these two variables, gender and college math experience. Do you think that gender predicts college math experience? Do you think college math experience predicts gender? Here's a note for you, by the way. Nothing predicts gender. Right? Knowing the two, gametes that form you may have, but that knowledge is elusive at best. And I hope I got those terms right? So, but yes, I'm going to predict why you are biologically a woman doesn't really do that, right? How many courses you took in college? There's a causal thing here, and it's not that, right? So we know that this could happen, and we know perhaps this could happen. Let me just walk down the line here. Let's think a little bit. I'm trying to engage in this discussion to think a little bit more substantively rather than just blindly throwing things in the model, because that's bad. College math experiences, typically the number of credit hours you take in college math is dictated by your major, right? You have a general ed requirement that everybody has to take, but beyond that, variation in it typically fluctuates based on major. If you're, I was a psych major, and my psych major did not require any math outside of the general ed requirement. I was a minor in statistics. That required a heck of a lot of math. Right? So I took a lot of math, but I'm a little abnormal. Do you think there is a gender effect in the selection of majors where math might be prevalent to it? I would say, unfortunately, yes, and hopefully with all of the effort that we're looking at now, we're trying to get more women into STEM or mathematics-needed fields. But yeah, I think historically that's the case. Heck, it was actually, I picked psych because of math to begin with, too. So I was counter to the trend, but that happened for me too. So anyway, I'm arguing why we might be able to add a direct effect between gender and college experience. What do you think?
Wouldn't it actually be an indirect effect that's mediated by degree?
Absolutely. If we were to have some type of degree program right here, right, we probably have something like that. Yep. But we don't have that. And but yes, absolutely. It's all indirect in this case. They're proxies for something else, which is really just how much math did you take? And I think they want a gender in there because, this is 94, we were studying issues with gender in mathematics. And they're not saying, well, gender directly affects performance. Really, gender, you may see a difference in gender on performance, but it's through these other things. That's really where they were going with this. But other thoughts, questions? That's ridiculous. I don't know the answer to that either, because maybe 94, maybe in the late 80s, you could pick a different vocational path in college. I don't know. High school. I don't know. I went through high school. 94 is the year I graduated. That tells you how old I am. And my high school made it so that I could swap out a year of science either chemistry or biology or physics for auto shop. All right, that was like the last year that was possible. And so I know this because I failed chemistry in high school. All right? The same year I took auto shop. Yeah. I know how to party. And, or I used to at least. But those, they would always say, oh, you got to take another science. I'm like, no, I can graduate without taking another science. I can just, auto shop counts. So what I'm trying to say is back in the dark ages, we had these things where like auto shop was what you were going to do, and so you did that in high school. I feel bad for the professor whose brake job I screwed up, or the teacher whose brake job I screwed up. But it was that type of learning experience. So maybe that was at the time. But I think now I don't know that we would have that. I think we would get back to your point, I think gender would not have an effect on it. And actually, hold on, let's go through the rest of it here. So we're going to find that actually when we add the effect of college math experience, neither of them are significant. Or one of them, actually college is, but high school isn't. So we flip the result. So we have these modification indices, and we had the residual covariances. So what we're going to do is add those two paths. Actually, we're going to add a path at a time. We're going to add the residual covariance first, right here. Right. Modification indices are 1 degree of freedom tests. So you may see a lot of them large, but the way they work is you add 1. And because parameters are all related to each other, once you add 1, you may have a lot of them get better. So 1 at a time. So we add 1. Here's our model fit statistics. We're speeding this thing up. We know how to evaluate model fit now. Look at that. Our model fit compared to the alternative or the saturated model, there's a p-value that's greater than 0.05. We want this greater. That means model fit. Right? The only p-value you want bigger than 0.05 is when your model fits. You do not want to reject your model. Right? The RMSEA is 0.048. That's very small. The CFI and TLI are very large. Looks like we've got good model fit. Pretty awesome, huh? Actually, I lied. In the previous analysis from the other year, I went down the deep end. I actually looked at the residual covariance matrix. I found still a big residual covariance between gender and college math. I added that path, which made this path go non-significant. So then I removed this path, and then I evaluated that model. So it actually, if you wanted to go with probably a better practice, it would be to go and keep going, even though you have good model fit, still look at your residual covariance matrix, still look at your modification indices. It may suggest something that may not be there. But if you're like me and just taking a cursory glance at these data, the fewer things you do to modify to get good fit, the better it usually is, because I don't know the field as much. Okay, so here's our parameter investigation, actually. Standardized parameter estimates. Interpretation. Let me just get here real quick. Yeah, there we go. Just double checking. Oh, template. I did it again. Somehow when I hit arrow and function, it gets me back to the front, and I don't want it to do that. There we go. So we can look at the parameter estimates now. We can look at the standardized parameter estimates. We can interpret them all the way we would for each of these regressions. Right here, this is the dependent variable, and these are the things predicting it, so these are the beta weights. The unstandardized is on the far left-hand corner. The standardized is in the right-hand side. Right? Interpret those just as we would before. I'm going to skip through those. Here we use the standardized no X example for whenever we have gender. Right there. That talks about the standard deviation increase in the dependent variable, or the difference between standard units of dependent variable for values of gender. So in this case, men are 1.66 standard deviations higher than women in math self-efficacy. Bless you. And the same thing, men are 0.075 standard deviations higher than women in high school experience. Not significant for the latter. Questions? Okay, here comes the fun part. Here's the interpretation. Forget that. Sorry, that's not fun. Sorry, that is fun. That's how you get your PhD, right? Once you get all that happening, everybody wants you to interpret them and make a big picture and go from small to large or whatever, Awesome. Cool, we did all that. We have our R squared for each of these. Some R squared is 0.573 for performance versus like 0.006 for high school experience. But that makes sense. High school, there shouldn't be a lot of variation in high school experience in math, right? You have high school curricula that are pretty much the same, even back when these data were collected. But here's the thing I want to talk about that's a little bit more interesting. Indirect paths. All right, so because high school experience predicted college experience, and because college experience then predicted math self-efficacy, we actually have an indirect path existing in our model. So this is just taking a little snippet of it. Think of it. So here's a picture. Right? Here's math self-efficacy. Here's high school math experience. Here's college math experience. Right? So we can look at math self-efficacy, and we can see as a dependent variable here that for every 1 unit, these are unstandardized effects, but I could do the same for standardized. But for every 1 unit more increase in high school math experience, math self-efficacy went up by 4.1 points. Right? But here's the thing about indirect effects. Right? While we were increasing high school math experience by 1 unit, what was happening to college math experience? College math experience went up 0.662 based on its regression effect, right? So if we were to go and say, oh yeah, by increasing high school math this much, math self-efficacy, yeah, it went up 4.13 points, 138 points directly. But now, because college math experience went up, we also have to incorporate what happened to it indirectly, right? Because as college math goes up, right, for every 1 unit increase in college math self-efficacy goes up 0.393 units. That's crazy, right? So, we didn't go up 1 full unit of college math, did we? We went up 0.662 units. So if we go up 0.662 units of college math, we actually go up that number, 0.662, times the direct effect of math self-efficacy. And this term right here, the product of the two beta weights, is what's called the indirect effect of a term, right? Because high school math had an indirect effect on math self-efficacy, what we're basically saying is for every 1 unit increase in high school math, indirectly, or through college math self-efficacy went up by the product of those two numbers, right? And that's the difference between direct and indirect, right? The direct effect is what happens directly with 1 unit increase. The indirect is what happens through all the consequence of all the other terms in the analysis, right? So here, high school math predicted college math. We went up 1 unit here, so college math went up 0.662. So the question is, if we go up 0.662, how much do we go up here? It's 0.662 times that beta weight. Just like you plug in a value for the x-variable, right? That's how it works. So the indirect effect is the product. The direct effect is just the estimate. The total effect is the sum of these two things, the estimate plus the product. So this answers one of the questions in the quiz. What would be the total effect of x on y? It's the indirect, or all of the, if you had another variable, it would be all of the indirects plus the direct. And this is what gets used in mediation analysis. Jennifer, it's the test alert again. Every hour I get a test alert. Anyway, shush. What we talk about here often is that when we look at this type of analysis, we may sometimes think that college math experience might mediate high school math experience effect on math self-efficacy. So this is sometimes we call the mediation model. Anyone ever heard of mediation? Mediation big in your field? Yeah. Mediation is just regression. Regression, my wife always says, regression was a better marketing campaign. Are you going to do mediation or moderate? Oh, gosh. Anyway, sorry. Nobody in a lot of the statistics fields uses the word mediation. indirect effect. That's usually what we talk about here. But for us here, this is our analysis. So you can calculate these by hand, but you can also do them in Lavon. To do this in Lavon, you have to first label the parameters. Right? So before we knew our direct effect, if we wanted to talk about the our indirect effect was the product of the slope of high school experience on college times the slope of college experience on math self-efficacy. So we have to go into our analysis and just put those things in as labels. This is what we did in homework, the last homework, for how we labeled the variances to make them equal. We can label parameters and not make them equal. We can just define different values of them later on to do what we want to do with them, in this case mediation or indirect effect. So here, I guess in my homework, just doing it. In my homework, shut up. I gotta get a new phone, I'm telling you. I had parentheses around the label. You can just put the label in by itself. So this is B underscore HSL underscore MSE is my label. This B CC MSE is my label. I then, in my syntax, in the quotes in my syntax, can add a parameter that represents the indirect effect that I'm looking for. And you'll note that parameter, the thing that, it's not a tilde now, it's a colon and an equal sign. Right? So the colon equal sign says I'm creating a new term out of these labels from before. So that's the indirect effect. The total effect, again, is the direct effect plus the indirect. So I just take this term over here and put it down there. But again, I'm using the colon and equal sign to make that work. I'm saying this because this will matter in homework this week. And I am going to get through this lecture. And I am going to talk about homework too. Okay. I don't want to scare you. This is not trying to be scary. It's more just I'm trying to connect it to something in literature. So I took a paper. We're going to do an analysis. All right? Replication almost. Questions? So in a path model that looks like this big thing right here, I just took a snippet of it to do direct and indirect effects, right? I just took this little 3-variable set. We could create indirect effects through the whole thing. Right? I could ask you, what's the indirect effect of gender on mathematics performance? That would take a lot of tracing to get out there, but we could do it, right? It would be the gender slope times this slope. That's one of the indirect effects. And then we'd have to add to it the gender slope times the math self-efficacy slope. That's the other indirect effect. Right? There's a lot to it.
So there's also gender through math self-efficacy, math self-concept, mathematics performance. Is that also one?
This could be one. Yes, it is. It's a little bit more questionable with it because gender only goes into 2 directions. But yes, it could be considered that as well. I mean, what we typically do with indirect effects is take where it starts and trace the path to where it ends. But this other part of it right here, this high school to college to math to whatever, that usually is thought of as the indirect of high school with that being there. Not usually, no. This is where being precise with language helps. Like saying what is the indirect through high school math versus the indirect by itself or something along those lines. But I've seen it. So I guess my ambiguity is saying I've seen it written both ways. But generally speaking, if you're talking about an indirect effect, it is you have to start with all the paths that emanate from that variable itself and just trace them to get to the variable you're looking for. So yeah, you could have a lot. You could be sitting there in direct and indirect effect trauma. So there's a lot to this. In fact, there are entire courses on mediation, as you would imagine. I am glancing over it. This is not the purpose of this course. But how we get our p-value is one of the problems in mediation. As you well imagine, remember the Wald test? The Wald test is estimate over standard error, and that thing should be normal. If your indirect effect comes from a product of things that should be normal, the result won't be normal. And so this Wald test starts to get a little wonky, weird. So in order to make it less weird, Levon actually does this for you automatically. It uses something called a bootstrap to give you your p-value, which is sort of the kind of the way that we report p-values in mediation these days. It's a bootstrap approach. It does it. It reports it as a Wald test. Just report it. Use it as you would, but its pathway to get there is a little bit more detailed. It basically takes samples of your data and replicates your model from it. It does that over and over and over again, tries to find a distribution for this indirect effect, and then tries to figure out what percentage point it is in this distribution of the indirect effect. Complicated. It actually works out pretty well because before, like if you're using M+ or some other program to do this, you have to go out of your way to make a bootstrap work. Levon just kind of automates it for you, which is nice, I think. Anyway. So additional considerations. Mainly, the thing about it is that we really need we assume that our variables were all continuous and multivariate normal or conditionally MVN and measured with perfect reliability. And in practice, that's not the case. We had 4 or 5 scales in there. So next week, we're going to start talking about the scale side. We need to put the latent variables in. Remember our first week example? I had marital status predicting a sum score of happiness, the ASU model of happiness. And then I did it as a structural equation model. We've sort of just done the first version of it, where we just added things together and put it into a regression. Although we've done it with 7 or 6 different regression lines. It's a lot. Bless you. When we get to next week, we're going to talk about the first half, or the part of that model where we formed the circle. We said happiness is really not a sum of these things, it's some latent variable that's indicated by these 5 questions, and build a model around it. So actually, it's not just next week, it's the next 4 to 5 weeks. We talk about all the things that go into building what are called measurement models, or measuring these latent variables. So if we were doing this analysis correctly, each one of the scales, including the last one, would have a measurement model with it as well. Okay, finally about causality, and here's the big thing to note. You may see people refer to this as a causal model. There's nothing causal about it. Right? These are observational data, or actually they're simulated data that are supposed to go with observation. There's nothing that causes it. Causal is essentially kind of like a hypothesis. And the way I think about causality is just like I think about the alternative model and the null hypothesis, right? If you fail to reject your model fit. So if you say, oh, my model fits as well as the alternative or the saturated model, that's basically saying your hypotheses were, you didn't reject them. So that sounds good. It's plausible they're true, right? It's the same thing with causality, right? You have these hypotheses about the world that you're forming, some of which, if it truly were the case in nature that one thing caused another, you would observe data that look like this. But you cannot say it's definitely causal because you didn't do any direct manipulation of observational data. Like, to get to causality, you have to actually go the step further, have random assignment, have manipulation, experimental groups, and so forth to make this happen. And you didn't do that. So our result, you may hear people call being causality. What we can't do, we cannot rule out that actually is the causal process. Right? We basically have it said, well, yeah, that might be one of the things that's happening. It's still valid. But you can't say, yeah, this is what causes it. Right? It's just one of the possible things that cause all of the different regressions or the different results that you see. Does that make sense? Right? But if the model doesn't fit, causality can't happen, right? So if you reject your model, you say that is not happening. Causality couldn't happen because the reality is if causality could happen, then it would produce data that are inconsistent with what your data have happening. Right? So you can reject causality with these models. You certainly can't claim it unless you have the experimental design, and even then, a lot of conditions to make it work. And in most of the types of social science research that we do, we just don't have enough strong claims to do it. I've seen people masquerade path analyses, particularly when I was new to learning about this. I'd see the word causal, and people, you go from learning about experimental research versus correlational research. And I remember one of my professors even used to say, well, yeah, path analysis is a way we can sort of get causal information out of correlational research. And it's not true. We can reject it, but we can't do anything more than we would with any other type of observational or correlational research from it. So, that's me. That's why I say causality is kind of a dirty word. Okay. Wrapping up, distinguishing path models from multivariate regression models. By the way, I'm going to talk about homework after this slide here. The distinguishing for the label is that odd case where dependent variables might predict other dependent variables. Identification conditions, we talked about it. Counting, right? The T rule, and then no circles, no cycles. What's an indirect effect? It's the product of all the beta weights as you go along. What is a total effect? It's the direct effect plus all the indirect effects. And what are standardized coefficients? Those are coefficients that describe the increase in terms of standard deviation rather than actual units themselves. Are we good on all those? Awesome. So let's go to homework real quick. Homework is available online. The document. Oh, Alan, I didn't change this. You're right. I screwed this one up. There we go. So I will fix this again. There's a paper in our Dropbox folder by Tian, 2011. And it's a paper in communication research. I don't know where I pulled this from, but just grabbed it. There's a bunch of variables, and this paper describes two models, path model 1, path model 2, both with different endogenous and endogenous variables. Essentially, path model 1 is current and existing relationships and friends online, and path model 2 is new, right? And so I looked at this, and I'm reading the paper, and the first thing I said is, why would you separate those into two different models? One of the things I'm big on is if you really should do things in one model. Namely, because you may have these intercorrelations between parameters that change the world if you just kind of omit things. So if you work with me on like a dissertation or comps or something along those lines, a master's, I will always say, you may have all these hypotheses. I'll say, well, find the model that incorporates all of them into one and test that one model, because you end up getting a lot of approach. So that's what we're doing here. Actually, I start off and I tell you, go take a look at the analysis path for model number 1. What that involves is taking a look at the paper and looking at the diagram, the path diagram, and then replicating it in Lavon. The same thing for path model 2. Look at the diagram, replicate it, because I'm trying to get you to look at diagrams and try to translate those into statistics and vice versa. Right? It's a very important skill to have. But then the fun part of the homework, part 3, is to take both of those models and combine them into one. Right? You should be able to do that, right? Because in model 1 you have two endogenous variables that are not part of model 2. They're non-overlapping in terms of endogenous variables. So when you get to model 3, you'll actually have 4 endogenous variables, 4 things that are fully in there. So everything else can predict it. Model 3, though, what you'll find is it doesn't fit. Yet again, a case where I take data from a model and it doesn't fit when I do a simulation. This seems rampant, doesn't it? It seems where model fit, having these lax standards for model fit cause problems. But so what we end up doing, it asks you to go then add 2 residual covariances with the largest modification indices. Now that sort of breaks my one at a time rule, but that's just, I knew the result and I didn't want you to have to go one at a time through homework because that would take even more time and effort. So you add 2 terms, right? And at the end of all that, you can report on the results. You'll find the model fits, you can report the results, and you can call it good. Questions? I feel like some of you look scared, some of you look like angry. Most of you are kind of like done with class. Sorry it's been so long. Again, like it works, you've got 2 weeks. Start it as soon as you can and let me know if you need help. Office hour, you've got 2 sets of office hours too, and also I feel like I've gotten a good rapport with many of you in terms of sending code back and forth. So that also works well. If you have a question, give it a try. If you have code that you've tried, shoot me the code. Hey, what's wrong with this? I'm happy to help with that. That actually helps. I hope that goes pretty quick. So, what's that? Yeah? No. Yeah. So, all right. Then I'll stop. Thanks, everybody. Have a good rest of your week.